Hello there, welcome back. In the previous slice of physics, we looked at adding vectors geometrically, which gave us an idea of what the resultant vector might look like. And now it's time to be more precise. We're going to use vector components to add two vectors so that we get a mathematical answer for what the resultant vector is. So these are the two vectors I'm looking to add today. They're both placed at the origin of a coordinate system that's labeled x in meters and y in meters. So these are displacement vectors. A is 5 meters long at an angle of 40 degrees above the negative x-axis, and B is 3 meters long and lies along the positive x-axis. The first thing, as we mentioned last time, that we got to remember is that when we're adding vectors, we can't just add numbers. So we cannot say that A plus B is simply 5 plus 3 and so 8 meters. That would be wrong. Second, there's a temptation to add these vectors by completing the triangle, since we just discussed tip to tail and we got two lines here, and there's a tendency to just connect the dots here and say that this is A plus B. Well, that is wrong as well because we skipped a key step. These two vectors are lined up with their tails on top of each other, and when we add vectors we need to move the tail of one to the tip of the other. So let's see how that works. I have duplicated A and B over here, and when I grab B and move it so that its tail lands on the tip of A, and that gives me the answer of A plus B as this vector over here. Now instead of grabbing B and moving its tail to the tip of A, what if I had done the reverse? So I got A and B repeated here, and I'm going to grab A and move it so that its tail sits on B's tip. And when I do that, I've got my resultant vector from the original tail to the final tip over here. So you can see that regardless of if I move B's tail to the tip of A or A's tail to the tip of B, I get the same answer. So that's all good, but we want to get a numerical answer for what A plus B is. We want to know what its magnitude is and what its direction is. So that's where we're going next. So I've cleaned up the figure here where I show A, the moved B, and A plus B over here. And we want to find the magnitude, i.e. the length of this vector, and its direction, which would be specified in this case as an angle, this angle or this angle, for example. So the best way to add vectors numerically is to work with their components. So I've got vector A over here, and I'm going to break it down into its components. So I take the projection of A along the coordinate axes, and so this here is AX, and this here is AY. And I can do the same for vector B, where this vector B is along the x-axis, so that would be BX, and there is no BY. BY is simply 0 in this case. Once we break the vectors into their components, we would simply add the x component to the x component, the y component to the y component, and that'll give us the x and y components of the sum, or the resultant vector. So let's see how that works. I'm going to make a little table over here for myself. So I've got x, y, a, and b. So the x component of A, we know this angle and we know the hypotenuse, and we want the side that's adjacent to the angle. So I want the adjacent, I know the hypotenuse, the function that ties them is cosine. So I get cosine of 40 degrees equals adjacent, which in this case is AX, divided by 5 meters. And when I multiply both sides by 5 and solve for that, that gives me a value of AX as 3.83. By the way, let's pretend that all these inputs, the 5 meters and the 3 meters, were specified to two significant digits. So it was 5.0 and 3.0. So we want our final answer in two significant digits. The intermediate numbers I'm going to carry to 3 significant digits and then round only at the very end. So that's 3.83 in magnitude. But we want the actual vectors of ax and ay. And so we see here that ax points towards the negative x-axis, and the sign is very important, so we got to mark this as a negative 3.83. My ay, for the angle of 40 degrees, this is the opposite side, so I need the opposite. I know the hypotenuse, the function that ties them, is the sine function. So here I can set up sine 40 equals ay divided by 5, and when I multiply by 5 on both sides and use my calculator, I'll get a magnitude for ay as 3.21, again carrying one extra significant digit. And then I look at the picture and I see that this is a positive value because it points up, which is where the y-axis positive values are. So just to remind myself that I've taken care of the sign, I'm going to put a plus there. So those are the components of A. For the components of B, it's much easier. The entire B vector is along the positive x-axis, so the x component is simply plus 3. And I'm just going to say 0, 0 just to carry 2 decimal places there as well. And the component, the y component of B, there is nothing. Nothing in math is 0. So I've got that. So the components of A plus B along the coordinate axes are simply the sum of the components of the vectors that go into it. So all I got to do is add ax to bx to get the x component of A plus B, and then I got to add ay to by to get the y component of A plus B. So this is just a numeric addition because we've already taken care of direction in the signs. So when I add these over here, I will get a negative 0.83 for the x component and a plus 3.21 for the y component. Now if we look at our picture, the A plus B is over here, its x component is here, and its y component is here, and those numbers seem to make sense. I've got a small negative number for the x component and a relatively large positive number for the y component. So that's one way of defining this vector. I've got its components, so it's fully defined. But if we want to go back to specifying the length of this arrow and the angle, we got to do a little bit more work here. So let me reproduce the picture here. So there's my y component of A plus B. Here's my x component of A plus B. And I know their values. This is 3.21. This is negative 0.83 because it points left. And now that they're lined up tail to tip, their sum is simply this vector. And I've got a nice right triangle here. So the magnitude of A plus B is the length of the hypotenuse. So that's just the square root of the sum of the squares of the other two sides. The rest is done by a calculator, and you get an answer of 3.31, and I'm going to round it down to our two significant digits of 3.3 meters. So that's the magnitude of A plus B. I still need to specify the direction, and I'm going to specify the direction as this small angle over here, which in this triangle is over here. And if I call that theta, I've got tangent of theta. Remember, it's TOA, so tangent is opposite over adjacent. The opposite of that is 0.83. I'm going to leave the signs out of this because I only want this angle, so that depends only on the length of the sides, not which way they point. 3.21, which gives me theta is tangent inverse 0.83 over 3.21, which your calculator will tell you is 14.49 degrees, or rounded to two significant digits, 14 degrees. So there we have it. Our final answer is that when we add these two vectors A and B over here, the resultant vector we get is 3.3 meters long and at an angle of 14 degrees to the left of the positive y-axis. So in this slice of physics, we learned how to add two vectors numerically. The best way to do that is by using their components. First, we broke each vector into its components along the coordinate axes. Then we added all the x components to get the x component of the sum, did the same thing for the y components, and then finally derived the magnitude and direction of the resultant vector from its components. This is a useful skill you will be using several times throughout this course. Thanks for watching.